Right, so moving on. So this is about the de Broglie wavelength of a neutron. So you should know the equation for de Broglie wavelength, which defines the wave particle duality. So this is the de Broglie equation. Lambda is equal to Planck's constant divided by the momentum P. So the lambda indicates its wave behavior, and mv, the momentum, determines its particle behavior. So I take the lambda that is given here. A de Broglie wavelength of a neutron traveling with a velocity v is lambda. Okay, and if the kinetic energy E of this neutron is increased 4 times, and they're asking the new de Broglie wavelength. Okay, so if you are doing physics, you should be familiar with this equation. Okay, energy kinetic would be equal to P squared over 2m. If you are not, so try to familiar with this equation. This is how it is determined. So we write down this half mv squared as a separate mv times v. So v you can write in terms of the momentum p, and then we substitute here p in terms of instead of mv, and we get this particular equation. Okay, so what it says is they're asking the new de Broglie wavelength if the kinetic energy is increased 4 times. Okay, so that is the idea. So if my initial kinetic energy is ek, now I can take my ek dash as 4 times ek, right? So this will be my first equation, where I define ek is equal to half p squared over m. And my second equation would be 4ek half p1 squared over m, because this will be my new momentum, because if you change the velocity or the kinetic energy, there will be a different momentum now. So if I divide this by 2 and write down my new momentum in terms of p, my new momentum is 2p. Okay, so try to remember this. So what I did is I divide this and take the root. Okay, so take the root, then you will end up here, and I write p1 in terms of 2p. Right, now I come back here, because they say my initial de Broglie wavelength is lambda, that will be equals to h, Planck's constant, divided by p. So this will be my first equation again, and my new wavelength would be lambda dash, that will be equal to h divided by 2p. Why I put 2p? Because my new momentum is p1, which is equal to 2p. So if I divide these two, I will get that my new wavelength is lambda by 2, which is the first answer. Okay, so here it is necessary that you know a little bit of physics as well, because this equation in mechanics, we use this equation very often in the calculation. So it is necessary either you derive this one or you know this one, because this is the easiest way that you can do. Otherwise, what you can do here is, you know, here lambda is inversely proportional to p, right? So if you do that in that way, lambda is inversely proportional to p, you need to have a proportionality between p and kinetic energy, because kinetic energy is half mv squared, p is mv. So here also you see mv, and here also you see mv squared. So it is difficult that if you just keep this as ek and try to find a proportionality between p and ek. We don't know. So that is why I derived this equation, which will give that the relationship between ek to momentum is a square term. Ek is proportional to p square. That is why if I increase the kinetic energy by 4, you increase the kinetic energy by 4, your momentum will be increased only by 2, because there is a square factor. So that is why my new momentum is 2p. Okay. So if your new momentum is 2p, then your lambda is going to decrease by half. That is what I have written here. So this is the calculation, this is the argument. Okay, so you can do in both ways. Right.